Okay, welcome to day two. Today we're going to talk about something special called limits. So the idea of limits is something that you kind of have basically discussed in talking about end behavior and other ideas, but now we're going to use the real notation for it, the real correct way we talk about it. So let's go back to what we did yesterday. So yesterday we looked at this quadratic x squared function. We talked about the end behavior. We talked about as x goes to infinity is the right side of the graph, and as x goes to negative infinity is the left side of the graph. And we looked carefully at this right side. As I go farther right on the x, this graph is going up to infinity. And as I going farther on the left, if I go farther left, this left side is going up to infinity. And this was the notation we used yesterday and probably used in Algebra 2 a year ago. Well, what we're going to do is use something called limit notation. So limit notation is using specific wording, math way of writing things. And if you look at this, we're going to use the exact same idea that we did over here with the end behavior as x goes to infinity, the f of x goes to infinity, and so on and so forth. So we're going to use it in a math shorthand called limit notation. So if you look at it, it looks very similar. You see that it has as x goes to infinity, and it has f of x. Well, what we're going to say is that this is going to go to infinity. It says as x goes to infinity, where is that function going to? And this says, and that's the right side. And now we have the same thing over here as x goes to negative infinity, which is the left side. The function is going to infinity. So if we look at this carefully, this and this say exactly the same thing. This was the words that we used yesterday, kind of an algebra approach to it. And now this limit notation is really more of a calculus approach to it. And that's where we're trying to get to. We're trying to get to calculus. Okay, so we're going to use this shorthand notation called limit notation. We have the word limit. Underneath it is the x. It's telling you where to go for the x, and it says, find me the f of x or the y value. And that's what we're trying to do. Let's look at this next function that we did, this 1 over x, or the reciprocal function. Again, we had the end behavior. And let me draw. Remember, we had a couple of asymptotes here. We had x equals 0. We had y equals 0. This is my VA. This is my HA. And this is the right end behavior. And as x goes to negative infinity, that's my left hand behavior. And if you look at this carefully, it says as x goes to infinity, or as x goes to the far right, if I go farther right on this graph is leveling off to y equals 0, or f of x is equal to 0. The same thing as I go farther left, or as x goes to negative infinity, I'm getting closer and closer and closer to y, or f of x is equal to 0. Well, I'm going to use limit notation, and again, I have x goes to infinity is my right side, x goes to negative infinity is my left side, and as x goes to infinity, my function goes to 0, and as x goes to negative infinity, my function goes to 0. And like I said before, this guy here and this guy here are saying the same thing. They say exactly the same, except this is using limit notation. Now we also talked about these words as x goes to 0 from the right. So 0 from the right doesn't mean start at 0, x equals 0, and go to the right. It means start on the right side and get closer to x equals 0. So if I get closer to x equals 0, you notice my y value is going up to positive infinity. If I do it from the left side and I go closer to x equals 0, this graph is getting closer to negative infinity. Except again, I'm going to use my limit notation. Here we go. And I'm going to make this really big here so you can see it better. this notation here, this little plus sign means from the right side. And this little negative sign here means from the left side. So when I see this, this says as x goes to 0 from the right. Well, we said that was positive infinity. And this says as x goes to 0 from the left. This was, we said, was negative infinity. Okay, so we have to pay attention to notation. Math people like to write things in shorthand and in notation instead of using all these long words. You know, this is a lot to write compared to this special notation. So this is how we're going to look at limit notation as x approaches a. A is going to be some value. It could be a number, it could be infinity. So the idea is as x approaches some number a, f of x approaches, basically it's asking what y value is it approaching. That's what it's trying to figure out. So whenever you do these limits, it's telling you exactly, go to some specific x value and tell me what y value we're approaching. So we could also talk about the limit as x approaches a with a little plus sign, and that's approaches a from the right. Or we could talk about the limit as x approaches a with a little negative sign. That means x approaches a from the left side. Okay, doesn't mean go left, it means approach it from the left. So on this page we're going to talk about the difference between function notation and limit notation. Function notation is what you've been used to. It says f of negative 4. Well, if I look at this graph, here's negative 4, and I come over here and I see a solid dot there. So f of negative 4 is equal to 6, because I have an exact y value when x is equal to negative 4. That's easy to see. As opposed to my limits. Now the limit for this one isn't going to be too different just because the way the graph is drawn. But the idea of the limit as x approaches negative 4 of my function, and the function is all the stuff that's graphed here, is also equal to 6. But it's a little bit different here because it's asking what is my intended y value, as x approaches negative 4. So basically what it's saying is that it is saying as I get closer to x equals negative 4, I'm getting closer to y is equal to 6. That's what it's saying. Now it just happens to say that here because of the way the graph is drawn, because it's nice and continuous there and it's a solid dot. But we'll look at another example. The next example is, again, function notation. F of negative 3 is equal to, I go to 3 and I come here and I said no, that's not it's over here, is equal to 13, because there I have an exact y value when x is equal to negative 3. Now it's going to be a little bit different over here. So when I go to x equals negative 3, I notice for my value I had 13 because there's a solid dot here. Okay? In fact, I should put that down. There's a nice solid dot. Nice solid black dot. That's what it liked. As opposed to over here, I have this graph, and what I have to do is basically I have to look at the neighborhood around x equals negative 3. Here's my neighborhood. Around x equals negative 3. And if I notice, if I squeeze that neighborhood and make it smaller and smaller and smaller, I'm squeezing around the y value of 4. So my intended, again, is my intention y value when x approaches -3. And what I'm saying is we kind of have this neighborhood going on. So the idea is this, and we'll do more examples in a second. A solid dot matters when I ask about a function's value, a function notation. But when I do a limit question, even though it's asking for a y value, it doesn't matter if it's an open or closed dot. It does not matter. It's asking if what y value is it getting closer to? What is this intended y value? It never has to get there. No one knows the closest number to 1. It's not 0.9 or 0.999. No one knows. It's as close as you possibly can get to 1. Okay, and that's what's going on here. In this neighborhood, this y value is getting closer and closer to 4. It never gets there because there's an open circle there, but it gets as close as it possibly can. Okay, moving on to at x equals -1. Well, here's x equals -1. I'm looking at f of -1. That's the easy case because it's looking for a solid dot. And when x equals -1, I have a nice solid dot at y equals 6. Now, these limit questions are a little bit different because it doesn't matter open or closed circle. So I have -1 with a little minus sign from the left, -1 with a little plus sign from the right, and -1 with no plus or minus sign. That means from both sides. And we're going to talk about that in a little minute. So if I go from as x approaches -1 from the left, and what I should do is follow my finger. So here's x equals -1. I'm going to grab orange. Here's x equals -1. I start here at -1. I go to the left of -1. I find the graph, and I get on the graph. The graph is what's drawn in black, not the grid. And what I do is I follow my finger, and I get closer to x equals -1, staying on the graph, and I stop when I get to x equals -1. Now when I stop here at x equals -1, my finger is at the y value. Y is equal to 12. So that's its intended y value. Now, it never gets there because there's an open dot there, but it gets as close as possible as you can to y equals 12. So the closer I get to -1 from the left side of -1, the closer I'm getting to y is equal to 12. Well, I could do the same thing. What should I use? I'll use this orange. Okay. Now again, this says -1 from the right. So here I'm at -1. I'm going to go to the right of -1. I could go a little bit or far. I'm just going to go over a little bit. I go to the graph, and I stay on the graph, the black graph, and I get closer to x equals -1, and I stop when I get to x equals -1. Now, there's a closed dot here, which is great, but it didn't really matter. And I see that this value, this y value, is 6, because that's its intended y value. Now, that time it does get to 6 because there's a solid dot there, but it didn't matter if it was open or closed. And then finally, it's asking from both sides. So this is where I have to kind of put both fingers on this graph. Well, obviously, I can't do this on a video, but the idea is that I'm looking at the left side and the right side, and I see that here's my right side, here's my left side, and let's say my left finger and my right finger are not meeting together, so when they don't meet, I put down DNE, which stands for does not exist. And that's because the left limit does not equal the right limit. For something to be a limit, it has to approach from both sides. Like over here at x equals -3. See, here was the left side, here was the right side, and the left side and the right side met at y equals 4, or that little neighborhood. I can't draw a neighborhood around both the left side and the right side of the graph. Oops, that happens. I can't draw a neighborhood around both sides of this graph and think I can capture one specific y value. See, I can't shrink that neighborhood. I could shrink this neighborhood here to get around y equals 4, but I cannot shrink this neighborhood there. Okay, let me shrink this up. Now finally we're going to do what x equals 3. So x equals 3 is right here. You're going to pay attention to this graph over here. Let's see if I can bring it down so I can write on it. And I have this value, and this value. Okay, now I'm going to do the limits. And remember, limits are asking for a y value. So all of these results have to be y values. So this is 3 from the left. So here's 3, and I start from the left side, I get closer to 3. And look, I stop right here at y equals 11. Doesn't matter if it's an open or closed dot, I get as close as possible to 11. And then I do from the right side, that was from the left side, here's from the right side, and again I get to y is equal to 11. So what do I have in general? Well, again, I do have this neighborhood around x equals 3, and it doesn't matter how small, I can make this neighborhood right here, this neighborhood bigger or smaller, doesn't really matter. And it's going to always, this neighborhood that I draw here from the left side and the right side is always going to shrink around y is equal to 11. So in general, let me just get this back. The limit as x goes to 3 on both sides is 11 because of that neighborhood I could draw around it, or because the left side is equal to the right side. So for f equals 3, we had was undefined because there was no exact value there. The limit from the left side was 11, the limit from the right side was 11, and the limit in general, this is called the limit in general, from both sides was 11 because the left side was equal to the right side. So in summary, a function value is f of a number is looking for an exact y value. It's looking for a solid dot. If there's not a solid dot, you put down undefined. Now when we do limit values are still y values. So when I do the limit as x approaches a of some function, it is looking for the intended y value. So the intended y value does not matter if it's a solid dot or open dot. It does not matter. Solid dots and open dots matter for values, function values. You need a solid dot, but for limits, an open dot or solid dot will not change the result. But we do know that if I have the left limit equal to the right limit, then the limit does exist. Okay? That means I would have either a continuous graph or something that just had a little simple hole in it. But if I have the left limit does not equal the right limit, then I say the limit is D and E. It does not exist. That's because I have either some sort of jump in the graph or a gap in the graph, or I might have an asymptote. And we're going to go through examples on the next page and what I mean. So we have this graph on the right here for all these limits that we're going to do. And if we look carefully, that these, let's read the notation. Little minus sign, this means from the left side, it means from the right side, it means in general, it means both sides. This is the value question. These two together go to infinity and negative infinity. This is my end behavior. Okay, this is from my right side, this is from my left side, this is from both, this is my function value, and these two at 2 from the left and 2 from the right is where my vertical asymptote is at, right here. So if we go through all this, it says negative 3 from the left, here's negative 3, I go to the left, I come here, I come back to negative 3, it stops at 4, I go from negative 3, I go to the right a little bit, I go up to the graph, I go up to the graph here, and I come back to x equals negative 3, and I stop here, and I stop at a y value is equal to 4. And since I have the left is equal to the right, that means the two sides are meeting together. I have 4, but the value question wants a solid dot. And that solid dot here at 3 is way up here at 13. Okay, and we did this in the example. This is, as x goes infinity, that's the far right side of the graph. So I have to go far right. That means here's my far right side of the graph. I go farther, farther, farther right. This graph is leveling off to y equals 8. This is the left side. If I go far left, the farther left I go, here's my left side, the farther left I go, this graph is going up, 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 up to positive infinity. Over here at negative 1, here's negative 1. I go to the left a little bit. I come here. I go from the left side. I stop here, and I stop here at 12. Oh, that's the right side. I should read better. From the right side, I come to negative 1. From the right side, I come over here, and I stop on the right side. And right here, I stop at 6. And from the left side, this is the one I did before, I stop at 12. And since these two, the left does not equal the right, then this guy here is DNE. And if I want the value at negative 1, here at negative 1, I find my solid dot. My solid dot here is at 6. And here's my vertical asymptote. So this says on the left side of negative 2. This is the left side, this is the right side. So right here is negative 2. If I go to the left side of negative 2, find the graph, which is the black thing, and I continue and I get closer and closer, closer to x equals negative 2, I notice that this graph is going down forever to negative infinity. Now if I come to the right side of negative 2 and I go up and I find the graph, and there's nothing down here, I have to go up here, and right here is the right side, and I get closer and closer and closer to x equals 2, this graph is going up to infinity. Okay, so I have to draw on here because I'm doing it by video, but the idea is that I'm really just putting my finger on the graph. That's what this pink lines and blue lines and red lines all represent, is me putting my finger on the graph and dragging my finger to where I want my x value to go, and then telling what y value is right there, whether I get there or not. A nice little practice problem. If you're watching this video, you can pause it and try them on your own. I kind of label everything. This is negative 3 from the left. Here's negative 3. I come to the left. Here's negative 3. I come to the left of negative 3. I find the graph, and I come back to negative 3, and I realize my y value there is 0. Then I go to negative 3, and I go to the right of negative 3, and I go up to the graph, and I come back to x equals negative 3. I find my y value there is 9. Since the left side does not equal the right side, I know I put down D and E. And I look for a value, so I go to x equals negative 3 and I try to find a solid dot anywhere. There's no solid dot there, so I put down undefined. It says as x goes infinity, so that's the very right side of the graph. I go farther right on this graph. If I go farther right, I notice this graph is going up to infinity. And over here on the far left side, I notice this left side is leveling off to y equals, that's a negative 6. As x approaches 9 from the right, so here's 9. I go to the right, I bring it back here, and I realize I don't get there. I get very, very close to y equals 6. I do it from the left side. I come closer to x equals 9, and I stop again at y equals 6. I notice that my left side equals my right side. So that means in general, or both sides, I have 6. And over here, I'm looking for a solid dot here. Here's 9. I found my solid dot is at y equals 3. Now I have my vertical asymptote. Here's 6. On the left side of 6, I go left a little bit of 6. Come here, and I realize I get closer to 6. This graph is going down to negative infinity. And then on the right side of 6, here's 6, I go right a little bit, I find the graph, and I realize this graph is going up. As I get closer to that vertical asymptote, it is going up to positive infinity.